tomorrow I'm going to be at the University of Chicago. We just now heard a very nice talk on active materials. So to begin to tell you what I want to tell you, I want to first introduce the other component of my talk, which are metamaterials, right? So what's a metamaterial? And one way to think about metamaterials is that they are materials whose function, whose properties are determined by their structure or by their architecture and not by their chemical composition. So in order to see this, we can contrast, say, a normal material like graphene, which is composed of carbon atoms and whose properties are determined by the chemistry of those carbon atoms, with a metamaterial which is inspired by graphene in that it has simple components arranged in a honeycomb geometry, but those components are not atoms. And as a result, they can be on a different scale. They can be, for example, deformed in a different way. So this is work that I won't go into the details of, but I want to say that, for example, by straining this honeycomb lattice, you can endow this metamaterial with properties reminiscent of electrons in graphene, but now they will be mechanical properties for the control of sound. So in other words, you can use the structure of a metamaterial to control mechanical properties. And in this way, metamaterials lie somewhere between normal materials and machines. So a machine, like a train, is also composed of simple components arranged together in such an architecture to give it its properties, right, to make the train move. But there's a big gap here between this type of metamaterial and this machine, because a train uses energy, right? It has an engine that's necessary to perform its function, that's necessary for it to move. And so that's where the idea of an active metamaterial comes in. An active metamaterial is somewhere between a metamaterial and a machine, in that it's composed of simple repeated components like a metamaterial, but like a machine, it uses energy to perform its function. And what I want to tell you about today is a particular type of active metamaterial where energy is necessary to have this property, these so-called chiral edge states. And I will get to what they are and why we think that they're interesting. But before I get to that, let me first focus on how to realize such active metamaterials. Or in other words, how to go from a sort of a block of stuff with holes in it to something that really moves, right? How to activate matter. And the example that we're very much inspired by is from the group of Denis Barthelot at ENS de Lyon. And what they have is a system of colloidal electric motors. So these colloids use an electric field that's pointed out of the plane in order to propel themselves within the plane. And there is this mechanism that's quite exotic, in my opinion, called Quincke rotation, that's used in order to create self-propulsion. I want to go into the details here. I just want to say that, a single colloid, as you can see here from its path, will sort of self-propel in a given direction with some interactions with other colloids. And if you put many of these colloids together, then you get an active fluid. In fact, you get what's called a polar active fluid, because all of the particles tend to align, and then they tend to flock or spontaneously flow in a single direction. So this is an example of such a flock composed of many, many colloids. And then this motion, this spontaneous flow, can be controlled by controlling the boundaries, right? Controlling the confinement of the system. And for example, if you put this in a racetrack geometry, even though the flow starts achiral, at the end, the steady state is chiral. In other words, it differentiates between anti-clockwise and clockwise motion. So these are the components that we want to use for a metamaterial, right? We want to build a metamaterial composed of many annular geometries, each of which has this active fluid inside of it. But the question is why, right? Why are we interested in this particular realization? And the answer for that is topology, right? Topological states of matter. One way to think about it is these are analogs of topological insulators, but in mechanics, right? And what we want to do is to use this active flow to create topological states of matter that have these exotic properties like chiral edge states. And so this was work that was done in collaboration with Benny Van Zouden and Vincenzo Vitelli in Leiden, as well as Denis Berthelot in Lyon. And if you want to hear more details, more of the technical aspects of the work, you can read the paper online at Nature Physics. Okay, let me introduce to you the idea of topological mechanics, and in particular topological acoustics. There are now several realizations of these phenomena using very different components. And if you look in this movie here, this is a realization using coupled gyroscopes. So each particle here is a spinning gyroscope, and they're coupled in such a way as to create this metamaterial where if you push it on one side, what you create is this chiral edge state. And this chiral edge state has a few remarkable properties. One of them is that even if the edge is disordered, if it has these defects in it, the edge state will go around these defects without scattering back. It also propagates unidirectionally, right? There's no edge state going the other way around the boundary. And it always stays at the boundary. So these are the type of phenomena I want to consider. In particular, the analogy for active matter is useful to think about simple fluids, right? There are a couple of realizations using simple fluids for these chiral edge states. One example is where you have motors inside of a fluid bath. These are the rotators. Another one is where you have a metamaterial composed of circulators. So these are toroidal channels with fans inside them. And the fans propel the fluid around in a certain way, so they create a pattern of flow. And as a result, this metamaterial has chiral edge states. So the interesting thing here is that you need these motors, right? In fact, you need a motor at every component in this metamaterial in order to create a particular flow pattern. And the reason that you need these motors is that in order to create these chiral edge states, one of the ingredients is to break time reversal symmetry. So schematically, I'm illustrating this with a painting of Salvador Dali where time reversal symmetry is clearly broken. But to me, I don't think about it in this metaphysical way, right? To me, breaking time reversal symmetry just means if you film the system, you can tell whether you're playing the movie forward or backward, right? There's a clear arrow of time just by looking at the movie. So that's true, for example, for these colloidal realizations. And we can start to build metamaterials out of them that break this time reversal symmetry. So if you look at this movie, you can see a pattern of flow. And this pattern of flow was designed by coupling annuli together. So within each annuli, the fluid spins either clockwise or counterclockwise, but then they're coupled by having small channels between them. And so this coupling is antiferromagnetic, or another way to think about this is that it's self-assembled geared motion, right? These individual annuli act like gears that are engaged with each other. So as a result, the annulus spins in the direction opposites to its neighbors, and in this particular geometry, the flow is fairly stable, so you can try to make a larger metamaterial where you get this pattern of flow over larger scales. So, but then the question is still why, right? Why did we ask Denis to create this channel geometry, right? What's special about it? And in order to get to that, what I want to talk about are the density excitations in this metamaterial on top of the steady state. So what you see here is a particular steady state of the active fluid, and you can think about exciting it somewhere and then studying how density waves propagate in this active fluid. Yeah, so each colloid, right, is 10 microns. So this is actually quite large, but still, barely visible, I'd say. So these are Denise colloids, right, that I introduced her. So this is these are essentially colloids that are sedimented on a surface with an electric field pointing out to make them roll around. Okay, so density waves on top of this fluid. So in order to study these, we're going to study them numerically with simulations. And what we're going to compute are the equations of motion for, solve the equations of motion for this fluid on top of the steady state. And these equations are well known. They were written down by Toner and Tu over 20 years ago. And they have this form that may be familiar to people studying normal hydrodynamics, right? One of them is just the mass conservation equation. The other one is an equation that looks like the Navier-Stokes equations. But there's an important distinction here. So this equation, even though it has a derivative of a velocity, it actually comes from the relaxation of the polarization order parameter. So these are not inertial dynamics. In other words, in the colloidal system, where inertia doesn't play a role, you can still have density waves that propagate due to the coupling between this polarization relaxation equation and mass conservation equation that's sort of analogous to the way sound propagates in a simple fluid, the way that it propagates through the air in this room. So the point is that we take these equations, we linearize them around a particular steady state, and then we solve them. We solve the dynamics or find the normal modes. And before I get to the results of the numerics, which which don't give you much intuition for why the phenomena are there, I want to go into a particular scaling regime, make a particular simplification that doesn't apply in the numerical calculations, but nevertheless tells us something about the solutions to these equations. So it's this term, right, that gives you the, that's the new term, and that gives you the spontaneous flow. That's prohibited by symmetry in the Navier-Stokes. So in the simplification I want to consider, we consider only very slow spontaneous flows, right? Spontaneous flows that are much slower than the speed of sound. And in that case, the equations simplify further, and if you Fourier transform them into a frequency space, you get the single equation for a density wave in this active fluid. And this equation has a form familiar from quantum mechanics, right? It's the time-independent Schrödinger equation for a charged particle in a magnetic field. And the role of the vector potential is played by the spontaneous flow of these particles. In other words, the vorticity of the spontaneous flow is analogous to the magnetic field. And in that way, what we're reproducing is the analog of the quantum Hall effect, but for these mechanical systems. And in the quantum Hall effect is exactly this realization, a two-dimensional electron fluid in a transverse magnetic field. And it's the magnetic field that breaks time reversal symmetry here. So in order to create this mechanical analog, again, we need to break time reversal symmetry. And that turns out to not be so trivial. Just having spontaneous flow is not quite enough. So to illustrate this, we can contrast the square lattice, or maybe one of the simplest geometries you could come up with the Lieb lattice, which is the one that I showed you earlier. You see in the square lattice, if you reverse the arrow of time, you switch, these colors of the annuli, the right or clockwise and anti-clockwise moving annuli. And you can combine that operation with a shift of one annulus to get back to the same steady state. So in some sense, the square lattice as a whole doesn't break time reversal. But the Lieb lattice does. And one way to see this is that the Lieb lattice has an odd number of annuli per unit cell, and it has a net vorticity in its steady state. So when you reverse the arrow of time, you change the number of red and blue annuli, and you can clearly tell. Okay, so as a result of these different symmetry properties, the density waves in these two lattices have very different dispersion relations. So these are computed again by solving the linearized Stoner 2 equations. And for the square lattice, what you see is that there are these points that are highly degenerate. And this degeneracy comes from the presence of time reversal symmetry. In particular, this is a plot of the frequency of a wave as a function of its wave vector, or wave 1 over wavelength, in a particular cut, so in a particular direction. So for the Lieb lattice, this dispersion relation looks different because break in time reversal symmetry also lifts this degeneracy. And because this degeneracy is lifted, we get isolated bands, right? Bands that don't touch each other in general. And as a result, for each band, we can compute a topological invariant. So this is sort of on the technical side of my talk, and to me this is sort of a black box, right? You perform these calculations from the solutions. So these are the eigenvectors of the density waves, the normal modes. And you take their derivatives, and you take the curl, and you get something called the Berry curvature as a function of the wave vector for these waves. And then the remarkable thing is that if you integrate this curvature over a closed surface, which is the Brillouin zone, in other words, the space of all wave vectors in this lattice, then you get a topological invariant, you get an integer. And one analogy that you can use to understand why it's an integer is with the usual Gauss-Bonnet formula for a surface, two-dimensional surface embedded in three-dimensional space, right? If you integrate Gaussian curvature over a torus, you'll get, or any closed surface, you'll get an Euler characteristic, and that's an integer. The Chern number is analogous to that, but with a different curvature, the Berry curvature. And so it's a different topological invariant. Okay, so now we'll get to the phenomena. So what are the consequences of having this Chern number in the active fluid? All right, and what you can see is that, for example, if you compute the normal modes for a finite lattice, what you'll get is that in the gap between isolated bands, there are these edge states. And this is, of course, a normal mode, but you can excite these edge states in a dynamical simulation, as you can see here, by having a source at a particular frequency. Right? So what you have is the source where this arrow is, and what you're seeing are the density excitations on top of the steady state. And what you see is that these density excitations are unidirectional and chiral, right? They go around in only one way around the edge. They stay at the edge, and they're impervious to the defects in the edge shape. So these are the topologically protected chiral edge states that I mentioned in the beginning of my talk. They act as robust unidirectional waveguides for density waves in this active fluid. And their direction of propagation is determined by the steady state. Right? So if you change the steady state to its sort of reversed partner, what you see is that there's still a chiral edge state, but it just goes the other way. It has the same property, but the direction of propagation is determined by the flow. Now there's a simple argument that tells you, yeah, go ahead. Oh, fine. there's a simple argument that tells you why these chiral edge states are there. And this argument says that, you know, this Chern number in the bulk of the material is non-zero, and because it's a topological invariant, it can't change smoothly. However, it must change going from the bulk to the vacuum, because the vacuum is topologically trivial. So something singular must happen at the boundary. And what can happen in order for the Chern number to change is that the band gap that separates individual bands, you know, above and below the frequency of this mode closes locally, right? And if this band gap closes, that means that at this frequency, there is an edge state right at the boundary. So what's remarkable about this argument is that it doesn't take into account the geometry of the boundary, and that's why these edge states have topological robustness. They don't care what the shape of the boundary is, they must be there due to this topological argument. So okay, that's the argument for the existence of these states, but in general, in order to observe them, we need to characterize them a little bit further. And in particular, what's important about these edge states is their penetration depth. Right, so their penetration depth is how far they go into the material bulk. Here, there's an edge state with a large penetration depth. Here, it's a small one. And in order to sort of understand what the penetration depth depends on intuitively, we go back to the scaling argument in the beginning, where the speed of flow is much smaller than the speed of sound. And in that limit, we can get a scaling law for the penetration depth as the ratio of the speed of sound to the speed of flow, you know, times the lattice spacing. And the reason that this is important for us is it tells us why active fluids might be a good candidate to realize these edge states experimentally, right? They, in the other fluid systems, they haven't been observed experimentally, and that's because for simple fluids, it's hard to make a flow where the speed of flow is comparable to the speed of sound. And and that's the only way that the penetration depth will be small enough to observe it in a small sample. However, for active fluids, both of these are just hydrodynamic parameters. And so generally, the speed of sound can be comparable to the speed of flow. It is in the case of these colloidal rollers that I mentioned. And you may be able to observe these phenomena in relatively small samples. Okay, so I have how many? A couple of minutes? 1 minute. Okay, then I'm just going to conclude. I had a whole other part of the talk, actually, that's on a different type of active fluids. But if you want to hear about it, please come talk to me afterwards. So what I wanted to conclude with is to say that, you know, in general, microscale motors can power materials that exhibit exotic mechanical phenomena, such as these topologically protected chiral edge waves, as a result of the broken time reversal symmetry that comes about from having activity in the system. And if you want to read more about the details of these calculations, of this work, please refer to our paper. Thank you very much.